Hello, everyone. Just waiting for everybody to get in. And doing some last minute grading stuff. All right, looks like everybody's in now, or well, in the process of getting in. How's my video and audio doing? I've had a lot of problems lately.
It's good on this end.
Good, hopefully it'll stay. I don't know why, it's just all day yesterday, and then first thing this morning it was working beautifully, and then it went to crap. So anyhow, that's the nature of the beast, I reckon. I gotta get better internet service. Actually, weird thing is I had the Ethernet cable hooked up and it improved after I disconnected it. So now I'm thinking somehow my Wi-Fi is doing better than my Ethernet cable. All right, so I guess we can go ahead and get started. I've got 15 of you, and I think there's still 16 or 17 still enrolled. But what I want to do is give you a little intro to chapter 29, which actually, let me read the title. It's called Electromagnetic Induction and Faraday's Law. You can download, for instance, for free from Project Gutenberg, you can download Faraday's work, and it's highly readable because it's not, he did not do anything mathematical. In fact, that was his weakness, was he, was from a poor class, so he didn't get to go to college. He knew basic arithmetic, but he was a genius. But like I said, none of his stuff came out in terms of equations, but he was a methodical experimentalist. So every nook and cranny that he could investigate of every idea he had, he did, and then wrote it up in a book. And actually, I'm looking at it right now. It's called Experimental Researches in Electricity by Michael Faraday. And it's funny because your book's telling about what he did, and I happened to actually be reading that very section on it at the time, which is only 6% into the book. But it's really interesting. The only thing that makes it problematic is reading is every now and then you need to Google something to find out what permaguda is and stuff like that. There's terminology that we don't use and names of stuff we don't use anymore. The permaguda was like a stuff they covered wires in to keep them from rusting, because at one point they were using iron wires, or from oxidizing or just deteriorating over time. It's basically the predecessor to latex. I think permaguda was the word they were using. But anyways, you got little things like that. But other than that, it's pretty straightforward. And what he did was he was looking for ways in which magnetism and electricity were related, because he had already found out that when you had current running through a wire, you could take the wire, let's say the wire is going up like this pin here, okay? And you put a magnetic, or you put a current through this wire, and then you put a compass right here, and that compass would, and I'm right next to it, so, and then that compass would of course point this way. And then if you put a compass right here, it point this way. You put a compass right here, point this way, and you put a compass right here, it would point this way. So you could see that if you look down above, it was some sort of magnetic field lines going around this way. And of course, it got weaker and weaker and weaker the further out you got, which is exactly what we learned from Ampere's law. Ampere was the one that was able to put it in a, one of the people that was able to put it in a mathematical form where you could relate it to something else. But it wasn't necessarily written that way for us to use the way that that we use it. However, we can. The other part was the Biot-Savart law, which does allow you to use it like we use. In other words, the Ampere's law, closed integral v dot dl equals mu 0 I enclosed, is an integral that ultimately spits out a current. We use it in this weird way where we take a current and we take the symmetry of the physics of the situation and extract that magnetic field out of the integral. So I'm not sure that equation was meant to be used that way initially, or just that was an incredible afterthought. And the same thing with Gauss's law in integral form. But in reality, a lot of these were all in differential form anyways instead of integral form. So that might have been part of the reason that you wouldn't expect to use it that way. They gave differential equations rather than these integrals. So Faraday had already found that that was the case. So he thought there might be other connections between electricity and magnetism, not just that magnetic fields are created by currents. In fact, what he did was he took a current and wrapped it around a spool of iron, basically. So you take a round, like a belt loop. I like to treat it like those pilgrim belt loops that you did in grade school when you did your Thanksgiving play. You know, the pilgrims had these big gold buckles or whatever. Well, if you just imagine a piece of iron like that and it's a closed loop, basically what Faraday did was hooked it to a battery source, a bank, if you will, and then ran around one leg of the belt buckle and then ran back. So the current would go in and spiral around like this. He thought by having many, many turns like that, you'd have a lot stronger magnetic field. And he was right, because, you know, if you get, well, we saw it in Ampere's law, basically, it's proportional to the number of turns you have. So the more turns you have, the stronger the magnetic field is. And since you did it, wrapped it around a piece of iron, that piece of iron is very, very willing to accept magnetism, and in fact will even possibly intensify the magnetic field and retain it within that buckle. So he imagined a scenario when current was going through here, that the magnetic field might actually go down through the buckle, out this way, and then back up the other side of the buckle, and then back around this way. So you have sort of a magnetic field running around like this. So then on the other end of the buckle, he wrapped the current and then connected it to what we call a galvanometer, which is a device that goes this way when a current comes through it, and it goes the other way when a current goes through it in the opposite direction. No battery was in that side. And when he did that, he discovered that a current did not cause a current in the other one. So in other words, he hooked it up and he looked at it and it just read 0. But he was paying close enough attention that when he noticed that when he flipped the switch to turn the current on the left side on, at that instant, the galvanometer would deflect for just a split second. And then when he flipped the switch off, the galvanometer would flip the opposite way. So he actually realized, wait a second, it is going, but a steady current does not make a steady current. A changing current will make a current. So when he figured that out, that became what we know of as Faraday's law. And not only that, he went quite a bit quantitatively and gave us a concept of flux, where he basically said that the amount of current that you get out of that, or the amount of voltage, if you want to look at it that way, that's the way it's actually written, is directly related to the number of turns that the wire made around the buckle. It was also directly related to the area, the cross-sectional area of that buckle. So the buckle's, you know, round, going like this or whatever, and that little cross-sectional area, and it's directly proportional basically to the magnetic field strength. So if you had a stronger magnetic field, you get a bigger one. So with all that together, he was able to put together what we call Faraday's law. And let me write right quick, just so you'll see what Faraday's law is. Or let me just turn the camera off like a goober. Okay. So Faraday's law basically says that there is an induced EMF, which we write that symbol E, which we've seen before for voltage. And that's equal to negative d phi over dt. And that phi is the flux. Remember, we talked about flux and magnetism when we did Gauss's law. Well, there's a similarly defined magnetic flux, phi sub b, which equals the integral of b dot dA. So it's just like the left-hand side of Gauss's law, which is closed integral E dot dA, only this is just the magnetic flux without a closed integral necessarily. So what he found was that a changing magnetic flux creates a voltage. And this negative is actually something that's absolutely necessary, because if it didn't, you'd basically, if it wasn't negative, you'd be making a perpetual motion type machine. So for instance, when the flux would increase, that would cause a greater voltage, that would actually cause a greater magnetic field, that would actually cause a greater magnetic strength, which would create a greater current, which would create another, and so on and so forth. Whereas this way, this actually corrects it. And we often call this part Lenz's law. the negative means Lenz's law, whereas this whole thing is Faraday's law. Okay, so Lenz's law basically says, I will write it out like this. When there, well, that's a horrible looking word. When there is a changing magnetic flux and induced EMF will be created in a direction to oppose that change of flux. So it doesn't oppose the flux. That's the common mistake people make. It opposes the change of the flux. So that's critical, and that's sort of one of the fundamental physical concepts that we're supposed to get from this course. For instance, I use questions like these to screen out applicants for physics jobs whenever I'm trying to hire somebody for a physics position or for doing writing solutions manuals or any of that kind of stuff, that the kind of work I do. I pose certain conceptual questions, and if they can't answer them, then chances are they don't have a good understanding of physics, so I won't hire them. So this is one of those ones that I consider to be a low hanging fruit, if you will. If you can't answer this, you didn't get your class. So keep that in mind yourself. That is a critical thing. So now I'm going to go about explaining what it means. So you've already seen how flux behaves. Basically, if you have a loop of wire like this, okay, if the magnetic field is perpendicular to the actual area vector, so the area vector in fact would point out like this, where that's actually perpendicular to the plane that the loop makes. So if this were actually perpendicular to the surface or parallel, then you get a maximum of flux. So what that means is if we have the rectangle turn this way and the magnetic field points this way, we get no flux, because they're actually perpendicular. The A vector and the B are perpendicular to one another, and a dot product of perpendicular quantities gives you a cosine of 90, and a cosine of 90 is 0. If, on the other hand, it's like this, and the magnetic field, say, is like this, then you get B. Yeah, I've gone below the paper, haven't I? Thank you for catching me on that. Then the magnetic flux is equal to B dot A, which equals B times A times the cosine of the angle phi, say, if that angle is phi. And then, of course, if you get it where A is this way and B is this way, then the magnetic flux is just equal to B times A. because the cosine, of course, of 0 is 1. Does that make sense? So there's a lot of ways you can cause a change in flux. One of the things we do in our, normally when we have what's called our Faraday lab, is first off, we have a current running through a wire, and we can only turn it on for a split second because it's literally a short wire that's really thick and made of copper. And basically we put this short wire like this through a plexiglass plate with a little hole in it. And then we put compasses all around it. And we turn it on for a split second, and you can see all the compasses align. And then, of course, you can see them align the other way when we turn the current on the opposite way. But we just do it for a second because it's going to, I mean, it melts the wire otherwise, or we'll blow a fuse in the power supply. So that's the first part of Faraday's lab. Then we take another one, and we take basically a solenoid. And you remember what a solenoid is. It's that wire that goes like this. And we take yet another solenoid, and this one's connected to a power supply. And what we notice is if we insert this solenoid inside of there, the galvanometer sits still. But while it's actually moving, then the galvanometer will say move one way. And then when it's moving the other way.
Oh, we can't see.
Thank you. Then when it's moving the other way, let's say the thing's being pulled out through the solenoid, then the galvanometer goes back this way. But it's only when they're relative to each other. And the weird thing is, or the perfectly reasonable thing is, that it doesn't matter if I move this into that or if I move that onto it. Both things give the same result. So if moving it, the small one inside of the bigger solenoid causes it to deflect to the right, then actually taking the bigger solenoid and sliding it onto the smaller solenoid also moves the galvanometer to the right. Once I come to a stop, I'm back to that again. So no motion, no relative motion. You get that. And that middle mark on a galvanometer is 0, whereas this is high in one direction, let's say to the right, and this is high in the other direction, let's say to the left. So that's the way a galvanometer works. It does nothing when it's at 0, when it's straight up and down, but when you got a current, say going from the black to the red, it leans that way. When you got a current going from the red to the black, it leans that way. And really all it is basically they're using Faraday's law to make the galvanometer. You can basically take a coil, if you will, and run current through it. And because that coil has a current going through it, it creates a magnetic field. And the stronger that current is, the stronger that magnetic field is. Well, if you suspend that current carrying loop between two magnetic ends, it's going to try to move to make the potential energy the smallest. So it'll move this way if the current's going one way, it'll move the other way if the current's going the other direction. But the main thing is it's actually using Faraday's law in the process of doing it. And they had sort of just, had something like it to begin with. So this is the kind of stuff we do in our labs. We even would do things where you'd make a motor. So this is all, Faraday's law is all about how you make motors, alternators. In fact, your book has a really nice schematic of an alternator in it, so you can understand sort of how that works and how this applies to it. But it all comes back to this single equation, which is the induced EMF is equal to the negative of the instantaneous rate of change of magnetic flux. So in order to do things with that, or to make applications with that particular type of problem, or that particular law, you have to figure out, one, how to calculate flux, which luckily we've already done with electric flux. And then 2, you need to know how to take the derivative of that flux. And then 3, you need to know how to interpret the actual angles at which are directions in which the current will go. So let me give you an idea. Let me give you some examples on that. Say, I'm going to switch to another page because I've used a lot there. So one thing you might imagine is this. First off, I want you to be straight about what magnetic fields are. So let's imagine a bar magnet with a north end up here and a south end up here. Okay. Magnetic fields basically leave the north and enter the south. I've said before, they're like old people. That's the way I remember it. So in principle, the magnetic field line should be leaving the north pole of a magnet and entering leaving the north pole of a magnet and exiting the south pole. And then of course, you also got to remember that the north pole of the earth is actually a magnetic south pole. That's why the north end of a compass points towards the north. So keep that in mind. Now, if you imagine, for instance, a magnetic field pointing out of the page, remember these dots represent these circles represent arrows. So you can sort of imagine an arrow with a point like that. And then of course you have the little feathers along the side like that. So if you want to represent a magnetic field pointing out of the page, you put a circle with a dot in the middle because the dot represents the point. And if you want to say end of page, looking at the back, you'd see that. So that's why we're drawing that. Now, what I want you to do is imagine a scenario in which we have a loop of wire like this, and it's a perfect circle. Now what I'm going to do is change that wire to that. So it's still the same amount of wire, but what do you think's happened to the area? Increased or decreased?
Decreased.
Yes, the area is decreased. The magnetic field hasn't changed, but the area decreased, and the flux, remember, is the integral of B dot dA. If you have a uniform magnetic field, then it's just B times the area. So in this case, the flux decreased because the area decreased. So according to Faraday's law, a voltage and therefore a current should be induced. Okay, so what is the direction of the current induced? That's the big question. Remember, I told you, according to Faraday, according to Lenz's law, when there is a changing magnetic flux, an induced EMF, E, will be created in a direction to oppose that change of flux. So it's opposing the decrease of flux. How do you oppose a decrease of flux? Do you increase the flux or do you further decrease it? To oppose a decreasing flux, what do you do to the flux? Do you increase it or decrease it?
You do the opposite. You would increase the area to, yeah,
you increase the flux. Now, the problem is you don't have a lot of freedom of what you can do, right? All you can do is do the very thing that Lenz's law and Faraday's law says, which is create an electromotive force, which is going to create a current. So we would have no current going through this wire, but as a result of stretching it out like that, the flux decreased. So what it saw was a magnetic field coming out of the page and all of a sudden the magnetic flux decreased. So it's going to try to restore that by creating a current that will create a magnetic field pointing in the same direction as it used to point, right? So the magnetic field was already pointing out, and it's going to try to increase the flux by creating a current going around the wire so that the magnetic field points out. So which direction does the current have to go in a wire, this way or this way, to make the magnetic field from it point outward? Remember your right-hand rule. When you grab a wire with your thumb pointing in the direction of current, your fingers tell you which direction the magnetic field will go. So the magnetic field here points around this way. In other words, in a counterclockwise direction. So grab this wire in the front, I mean, at the bottom here, grab it right there on that bottom. If you put your, if you assume the current's going this way, which would be clockwise, then you see in the middle, my fingers are going into the page. So that creates a magnetic field going that way. Is that what we want? We don't want that, because that would cause the magnetic field that does exist to get even smaller. And we already have a problem with the flux decreasing. So if we grab it this way, say the current is going to go in a counterclockwise direction, then grabbing this wire, my fingers come through the middle of the loop like that. So they're pointing out there, and that means that is the correct direction. And I will draw that as such. So the induced current would actually be that way. Now that also means the induced voltage is such that this would be high voltage and that would be low voltage. Of course, that gets a little bit crazy, because when you get over here, it's got to change. But just at this particular point, this end must be a higher voltage than that end. That's what's making that current go around there. Okay. But as you can tell, we also work straight with the current, because the current directly causes a magnetic field, which is our ability to change the flux by inducing an EMF. Okay. So now let's look, what if I take, again, let's do a magnetic field this time pointing into the page. And initially, I'm going to have a different pen than the one I'm using. I'm going to have initially a loop of wire, and this has got a lot of different turns on it, so I'm trying to draw it like this. Okay. So that loop of wire is lying perpendicular, where its area is actually parallel to the magnetic field. Well, actually parallel or anti-parallel. In other words, the area is arbitrarily pointing in or out because it's perpendicular to the plane of it. What I'm going to do now is imagine rotating about this axis. So let's say there's a axle. Right here. And I'm rotating this this way. So the next time you look, I still have the same magnetic field. But now the circle looks more like an oval because it's turned to 45 degrees. Okay. So the first question you asked, did the flux change? What's your answer to that? And going from here to here, did the flux change?
Yes.
Yes. Okay. Your second question is, now if it didn't, then there's no voltage whatsoever. No implies no induced EMF. Okay. But you got, yeah, so we're not having to deal with that. Did it increase or decrease? So remember, the flux is this. The integral of B dot dA, that is what the magnetic flux is. So you see the ways it can change is B. B can change magnitude or direction, or A can change magnitude or direction. What in this case happens? Someone said it decreased. Is that correct? Does everybody else agree? So yes, it decreased. Okay, and the reason why is because the area vector, which was exactly parallel or anti-parallel to B here, is now, say, square root of 2. In other words, the cosine is √2/2, because we're now at 45 degrees from B. So now the flux went from B times A to B times A times the square root of 2/2. So it did actually decrease. So how do we fight that change? So your only tool at your disposal is the B through creating a current. So what are you going to do? Do we increase the flux or decrease the flux?
I think we increase the flux.
Yes, we try to increase the flux by increasing B by creating a current. Okay, so we're going to create a current in the wire such that the magnetic field that was pointing straight through it this way and is now looking weaker. We're going to try to reestablish that magnetic field by creating a magnetic field going that way. So which direction will the current need to flow? In which direction will the current need to flow? So in this case, we're looking head on. Is it going to go counterclockwise or is it going to go clockwise? So remember, to get this part, you've got to try putting your thumb in, let's say, in the upward direction on this left-hand side. And then that shows magnetic field going into the page in the center of this. Then you try, of course, the magnetic field going upward on the right, which is the opposite of what we just did, that would show the magnetic field coming out in the middle. So which one of those do we want to do? Anyone? Anyone? Okay, so in this case, remember we asked, did the flux change? Yes, it did. Did it increase or decrease? It decreased. Okay, how do we fight that? Well, we fight that using Faraday's law by introducing a induced current that will create a magnetic field that tries to reestablish what it had. Well, what it had was a magnetic field coming out of the page, and it still has that magnetic field coming out of the page, but because the relative angle between that magnetic field and the A vector has actually caused the flux to decrease, then it's going to try to establish a magnetic field just like the one it had, so that that can make it stronger again. So it's going to create a magnetic field that goes into the center, which means we got to grab it with our right hand, poke our fingers in through the middle, and then see what our thumb does. And our thumb is telling us it's going to go in a clockwise direction this time. So the answer is clockwise current. And just to make sure you see what I'm saying, we're going to say this is the loop of wire, and this is I going through it. And then, of course, the magnetic field, which before we drawn in black, but I'm drawing it in blue now. So because that's moved, it went from a complete circle to something tilted about a 45-degree angle. Really, the problem was the amount of magnetic field lines getting through there was less because the area was askew. Now it's going to establish a magnetic field by creating a current. Whoa, whoa, whoa. I said clockwise, and then I drew exactly the wrong thing. And why am I using my pen that I can't erase? Sometimes I make stupid decisions. Yep, that's what I drew the whole time, was clockwise. Literally, I wrote clockwise and then I drew it counterclockwise like an idiot. That's the problem when you wear digital watches. You forget which way clockwise is. Okay, so does everybody follow that? So the current always tries to establish a magnetic field. If the flux was increasing, it's going to try to decrease the flux by fighting the magnetic field with a counter magnetic field than what it had. If the flux was decreasing, then it's going to try to increase the magnetic field to what it had before. So that's the major rule. That's what Lenz's law tells us. So let's look at another one. Let's say now we're going to have magnetic field lines going into the page like so. And we're assuming it's basically uniform. That's why I'm trying to draw these at the exact same spacing and stuff like that. So what I'm going to do is I'm going to imagine now that I have a basic frame here. That goes way beyond the edge of the magnetic field. So the edge of the magnetic field is roughly here and here. And what I'm going to do is I'm going to lay a metal bar across it. Okay. I'm going to say this length right here is L equals 10.0 centimeters. And I'm going to say initially this distance right here to here is 1.00 centimeters. I'll call that L0, or actually I'll call that A0. No, not A0. I don't want to use A. That's stupid. I will call that W0. Okay. And we'll say this is a copper rod. Okay. Now I'm going to pull this with a velocity equal to 1.00 meters per second. And the magnetic field strength is going to be 1 Tesla. Okay, 1.00 Tesla. Now, I told you before, a Tesla is a big unit of magnetic field. A Gauss, for instance, is about what our Earth does, and a Tesla is about 10,000 of those. So it's pretty high. I think it's 10,000. Pretty sure. Anyways, all right. So what we're going to do is we're going to actually figure out what's happening with this. So I'm taking this thing, which is initially this metal rod is 1 centimeter from the end here, and I'm going to pull it horizontally to the right. And I'm going to pull it from here. Well, we can figure out how long. Basically, I can say that this distance from here to here is W equals, let's say, 100.0 centimeters. Okay. So what I would like to do is find out the induced EMF. So A, what is the induced EMF? Okay. I might ask some more questions in a second. I haven't decided yet, but what I'm going to do now is I'm going to realize that Faraday's law says that E is equal to negative d phi over dt, where phi is, of course, the magnetic flux. That's equal to negative d by dt. In this case, notice the A and the B have no relative change in position or in direction or anything like that. So basically, the dot product is just going to be B times A. But A is a variable. So we're going to say phi is going to be B times A. But A has a function of time. So can anybody tell me what the formula for the area is? Might even write it as A as a function of T, just to remind you there will ultimately be some kind of T in there. What is the shape, for starters? Can anybody tell what the shape of the area is going to be? The area is the thing enclosed within this leaf and within this thing right here. So we're saying basically that's the shape. So what kind of shape is that?
Cylindrical.
A rectangle, very good. And how tall is that rectangle? Tall from here to here.
It's 10, it's the length.
Yep. So I'm going to say L, just to keep it as a variable, because that way we'll get a result we can use over and over. But yeah, that is going to be 10 centimeters. Now, what's the width? Right now, that little thing says W0, but you know it's moving with some velocity. So that's not the full answer. I'll write that bigger so you can see it. Do y'all see that velocity, which is dx over dt, right? Do you see that the W will be this amount first plus that times t? So I'm going to say width as a function of time should be W0 plus VT. Does that make sense? So I'll put this in here. Okay. And by doing that, I now have the area as a function of time. So I can now say E is equal to negative d by dt of, I'm going to go ahead and distribute all this through. I'm going to get LW0 plus LBT. And that's going to be negative. When I take the derivative of LW0, I get 0. But when I take the derivative of LVT, I just get LV. So that's negative. Oh, excuse me. That was the area. I forgot the B's got to be in there too. So you ultimately will get negative B times L times V. So this induced EMF, putting in the numbers, is going to be negative 10.0 centimeters times, of course, 100 centimeters is equal to 1.00 meters. That will allow us to have the proper units. That's my L. I'll just leave the negative in there. I didn't realize I'd written it in there. That's why I got ready not to. Then I'm going to write 1.00 Tesla. And then I'm going to write the velocity is 1.00 meters per second. So the answer numerically is basically a negative number, but really all you care about is the magnitude of it. We're going to figure out the direction of the current in a second, and that's what the negative is all about. So I'm just going to go 10 divided by 100 is 0.1, and then I'm going to say times 1, and then times 1 again, which clearly I don't need a calculator for. I don't know why I grabbed my calculator in the first place. So that gives me 0.100 volts. So that's really what the voltage is, 1/10 of a volt. That's moving at a rate of 1 meter per second, which is sort of like this speed, right? And that's a strong magnetic field. So you can see this isn't a super effective way of generating electricity, but we did get it. So there's that answer to part A. Now, if I wanted part B, I could say the entire setup has a resistance. I don't know why I wrote resistance with a G, but I did. Resistance of 10.0 ohms. What is the current? So this is the part where I can decide which direction the current is going to go. So E, which is a voltage, is just I times R. So I would just be 0.0100 amps. So about 10 milliamps is all we're getting for part B. Okay. But now what is the direction? So in order to figure out the direction, remember we asked, is the flux changing? Is the flux changing, everybody, by this bar moving to the right?
I mean, it's moving.
Yeah.
Yeah, so the area is actually getting bigger, right? So does that mean the flux is increasing or decreasing?
It's increasing.
Yep. So the flux is going up. Therefore, a current is going to be induced to fight that increasing flux. In other words, it's going to try to battle and cancel out this magnetic field. The magnetic field right now is pointing into the board or into the page. So it's going to create a current that makes a magnetic field point out of the page to combat that increasing flux. So will that current need to go counterclockwise, or will it need to go clockwise? Okay, so if you imagine this being a loop, imagine, for instance, the bar being way over here so you can actually get your fingers around it. If I put my fingers in the middle downward, then I'm increasing the magnetic field. So I don't want that. I want to decrease the magnetic field because that's my method of decreasing the flux. So I'm going to create a magnetic field coming out of the page. When I grab that, when I stick my fingers through the middle of that, like I'm doing here, then I can see my thumb is pointing to the right down below. So in fact, the current's going to go around this way, which is counterclockwise. So that's part of the answer as well. Not only is it 0.010 amps is the current created, but in fact, the direction is counterclockwise. Does that make sense? Anybody have any questions on that? Okay, so now let's imagine another scenario. I'm mostly trying to get through the concepts right here regarding Faraday's law. A little bit of calculation right now. We'll have plenty of time to do calculation, obviously. And there's plenty of good examples in your book, but I want you to sort of think about the complexities of this issue. So let's imagine, for instance, we have an axle like this. And then on that axle, we have a bunch of wire. And of course, well, a bunch of wire, I mean a bunch of turns of wire. And on this side, we got some nice bearings and a thing to lock it in place. On this side, we have some nice bearings and a thing to lock it in place. But then out here, what you realize is Mr. Younger has connected this to like a grist mill or a water mill or something like that. And in fact, he might even use Tesla's design. You don't have to have individual planks. You can actually just have slits in here. So basically a bunch of discs separated by a very small distance, and the water flowing through here is going to cause all of this to rotate this way. Okay. So what's going to happen is if I put this loop inside of a very intense magnetic field, the more intense, the better, of course. So you can make save money by making the loop kind of small, and then the magnets don't have to be that big. But of course, making the loop small makes the area small. So that makes the flux a little less. And then of course, making the area big means a lot bigger magnet. So really what you try to do is increase the number of turns a lot, because each one of those individual turns gives a flux. So if you got n turns, you got n times as much flux. And what you do really is you try to establish a magnetic field. In this case, I'm drawing as if it's going into the page. So what you might imagine is maybe right on this side, obviously a little bit further than this distance from here to here, a little bit further out from there is in fact a north pole of a magnet that's rectangular in cross section. And then on the other side, that's just a little bit further than, again, this distance right here behind the page, that's going to have a very strong rectangular south pole of a magnet. So that's going to make a fairly uniform magnetic field. And then you can have the wires come out, and there's little mechanisms, stators and things like that. that actually can allow you to tap that current while that wire doesn't get wrapped around the axle. In other words, this wire will come up and touch a sleeve that's stuck around it with bearings, and then the other wire will come around and touch another sleeve that's attached with bearings, and one end will be the positive voltage and the other end will be the negative voltage. But by the nature of this, what you're going to see happen is that the magnetic flux is going to be approximately N times B times the area times the cosine of the angle, which is going to constantly change. So that's going to be omega t, like this. Okay. So in other words, the angular frequency here, omega, is equal to 2 pi times f, is where this is rotating. So this thing's going to rotate like this. And because of this, it's going to be a maximum in one direction when the area vector is perpendicular to this. Well, the area vector is always perpendicular to the face of the loop, but when it's actually parallel to the magnetic field, depending on which end you tap as positive and which end you tap as negative, what you're going to get is a graph of flux that looks like this. And actually it should actually be, since I decided to model it with cosine, I should do it like this. Okay. So that's actually your magnetic flux as a function of time. And of course, this is one period. And of course, a period is equal to 1 over the frequency. And of course, the frequency is omega over 2 pi. So I'm going to be 2 pi over omega is what that t is. So what's going to happen is when the A vector and the B vector are parallel, I got this. And then it's going to rotate through 90 degrees, which means the loop is like this now. In other words, the area vector is pointing up. Or actually, in this case, it should be pointing down. And then now it's going to be pointing out of the page, and that's going to bring it to this point, or excuse me, to this point. So I should get rid of this because I drew that one funny. So I think you can see that naturally with this type of electricity generation, you're automatically going to get a sine wave, right? When we get back to 90 degrees again, this time we were like that before. Now we're like this again. Now the area vector is actually pointing up, and that's where I get to 0 here. And then we're back to where we started from. So we're here again. Okay. Well, that's going to be what the flux is. So then you get E is equal to negative d flux over dt. And I'm going to stop writing in red because I got red written under it. So I'm going to get E is equal to negative d by dt of n times b times a times cosine omega t. And of course, the derivative of cosine is negative sine. So I'm going to get positive nba sine omega t. So we're actually going to get a voltage now. This, by the way, this value right here, which is b times a, where a is, let's say, L W, where a is equal to times W. Okay. Now, if we make a plot of voltage as a function of time, now it's going to look like this. Notice it's out of phase with the flux by 90 degrees. And this peak value is going to be N times B times A. And of course, this period is going to be 2 pi over the angular frequency. So whatever rate at which you can turn that mill, that's going to set your frequency. Then you can do electronic stuff, use electronics to actually adjust that frequency to the exactly the 60 hertz that we use in everyday life. But that's how you can make a generator. So anytime you have a current carrying wire, and some ability to rotate in a magnetic field, you can generate electricity. And that's, you know, an easy way for you to make a self little charger, for instance, for your cell phone. You just have to know the specs on what your cell phone uses. Your cell phone actually takes a AC signal, converts it to DC, or actually your cell phone charger converts it to DC, puts it at, if I remember correctly, it's 5 volts, and it runs at about 0.82 amps when you first plug it in. It's dead empty. So you try to lock that down to 5 volts, and then that should actually provide the current that's necessary. So long as you have a circuit after this that can break it down. And the way you normally do that, by the way, is once you calculate what this N times B times A is, that's the particular voltage that you get, right? That voltage might be 12 volts. That voltage might be 782 volts. Well, what you do is you take that source and you run it through a resistor, R1, and then you run it through another resistor, R2. And ideally, if one of these are actually adjustable, that's the best case scenario, because it turns out when you have a current I going through here, then the total voltage across here, V total, is equal to V total is equal to I R1 plus R2. So you see that I would be V total over R1 plus R2. Now all you have to do is realize, well, the voltage across R2, V sub R2, is actually I times R2, which would be R2 over R1 plus R2 times V total. So you make sure that this quantity right here gives you 5 volts. Then all you have to do is take these 2 leads and connect them to your battery. That's called a voltage divider. Later, when we learn about diodes, I can tell you how we'll take this and turn it back into a DC current. But basically, you can imagine it this way. If you come in and this is the high voltage part, then this voltage is going to run right through here. But if we allow something that only allows stuff to go one direction, like that, then this part right here will come through as a bump. But this part right here will come through as a flat line, because this doesn't allow negative current. But then this part here will come later and you can get that. Well, if you now take the negative side and do the same thing, where you're only going to let it come through this way, then this side will come out and get unlined, and then a bump, and then a flat line, and then a bump, like that. And therefore you add those 2 together, and out you get a signal like that. So that's your voltage as a function of time. Now, if you then take this and just connect it to a capacitor, then that's going to cause this voltage change to delay sometime. As we've seen, capacitors charge up and then discharge, but they take a finite amount of time. If you adjust that and, you know, even some resistance here, then what will happen is that voltage will come up, and then when it gets right here, it's going to try to fall, but the capacitor is going to slow it down, and it'll do this, and it'll only maybe get that far down before the next one comes up. So don't go like that, and it'll go down. And if you ever get a chance to look at an oscilloscope for a DC full wave rectifier, you'll see that it basically looks like this. And that's your that's how you basically make your AC signal into a DC signal. This is called a full wave rectifier when you have two of them. A half wave would only give you one of these signals. And then of course that would be way more wiggle. But anyways, that's it. That's the crux of what we're doing regarding this. So does that make sense about how you can make electricity? So if you've got any ability to rotate a wire that might carry current between magnets, then you're golden. If you actually take and look at just at, say, a push mower. I pulled my head of my push mower off the other day. You know, you pull the rope on the push mower and that thing spins around. Well, just take a metal wrench. If you pull that turning thing out, take a metal wrench and run it around the sides and it'll get stuck at a couple spots. What that is a magnet in there. So you've got an internal combustion engine, namely the engine, the two-stroke engine or that you have for the lawnmower, that's making a source of spinning. You're getting it started by pulling it, but then the engine combusts and causes explosions to push a piston that turns a rotating shaft, and that rotating shaft causes things to rotate. So if you take that and connect a magnet to it, then you're creating basically a magnetic field that changes. Now, if you put a little wire anywhere around it, it's going to generate a current changing through it. That's exactly what they do with a car motor, a car engine, I should say, because they have that spinning, camshaft at the very bottom, and you can tap into that. And in fact, that's exactly what the belts are for. The belts take that rotation and take it other places. Like one of the places it takes it is to a little pulley on the side of the engine that is your water pump. And that's just got a little blade inside. You know, people think a water pump, if you've never done this kind of work before, people think of a water pump as if it's got some kind of, like compressor and pipes and all this stuff. No, the water pump is basically just a series of, well, it's connected to a series of tunnels through the engine block. And inside of that little spot in the engine block where a pulley is attached, that pulley is spinning a little blade. So the water pump's literally just a little plate with a blade on it that spins around like this. As it spins, it causes the water to circulate because it's got a high pressure side and a low pressure side due to the shape of the blades, and that just pushes water around it. They also take that same system of pulleys, and one of the pulley belts goes around another ring, and in this case it looks like a big washing machine engine or something off to the side. In that case, that's the alternator. And if you look inside there, you'll see a bunch of wires pulled around. They again have a magnet in there spinning around a bunch of coils of wire. That's keeping your battery charged. And in fact, if your alternator's dead, part of the electricity going to your lights, of your headlights and stuff like that, and your radio, all that stuff's coming from your alternator too. The battery can do some of it, but it doesn't do very much of it. Normally the battery is just there to get you started, and then it provides a little bit of electricity each cycle for the spark plug. If you have a diesel, you don't even have a spark plug. You just have a compression ratio that's so large that the gas gets so hot it explodes by itself with no spark. So with a regular engine, you actually have to have a spark, and that's what spark plugs are. They're nothing electrical about them. It's just a piece of metal with a gap between one piece of metal and another piece of metal, and insulation separating them until the very end. There's a little bit of air, or in the case of where it's at in the engine, there's a little bit of gaseous air that might have nebulized gasoline and air mixture in it. When a voltage gets across on the little leg across that to the ground part, then electricity will jump like a lightning bolt, and that actually causes an explosion. So some of that electricity can come from the battery as well, or the alternator. But basically the alternator and the battery is supplying all the electricity, and the alternator is constantly trying to keep your battery charged. But that's all being done by the fact that you had something rotating. So anytime you have something that can make something rotate, you can either rotate a coil of wire in a magnetic field, or you can rotate magnets inside of a coil of wire. Both of them produce electricity. Not only that, there's a cool thing. People have been caught doing this. By the way, the power company is very smart. They know how not to get robbed. So I will tell you this cool thing that you can do that you should not do because it's illegal and it's kind of dangerous. So if you go out in the country fields where they have those cool headless dude looking towers, they literally look like people, but without heads. And they got these long power lines connecting them like that. Those are high voltage. And we'll learn later in this chapter where we do the, basically we're going to do the transformer equation. And the transformer equation says, hey, if I'm going to send out electricity from a power plant like that mill I just showed you above on this page, if I'm going to send out power to a neighborhood, if I have 200 houses, I know each house needs a 200 amp service. That's average what a house uses. Then I have to multiply 200 times 200. So that actually gives me what, 40,000 amps. So I've got to push 40,000 amps across here. And I only want it to be about 120 volts. Well, it turns out from the transformer equation, if you step the voltage up from say 240 to 240,000, you've jumped it up by a factor of 1,000. That means the current is going to jump down by a factor of 1,000. So instead of 40,000 amps, you now only need 40 amps. By doing that, they've now made the voltage jump up here to 240,000, say, and it's normally on the order of 500,000, a million volts, stuff like that. And it's still a buttload of current. It takes a milliamp to kill you. So we're talking 40 amps here, and that's for a small neighborhood, by the way. But anyways, this voltage going across here has been jacked up really high because it turns out that the power loss due to these wires is I squared R. P equals I, well, the original formula was P equals IV, and then if you put V equals IR, you get I squared R. So you see, by cutting the current by a factor of 1,000, you've just decreased your power loss by a factor of 1,000,000. So that's why they run high voltage. Well, the other thing about that is, well, guess what? With all this current going through here, you're creating magnetic field lines going all around like this. So oddly enough, you can still generate power and you don't even need anything rotating, because all you got to do is just, in the darkness of the night, again, not recommending this, this is highly illegal. Okay, in the darkness of the night, you can make a big loop of wire like this, thousands and thousands and thousands of turns, and you can steal electricity from the power company. Now, again, they're very good at this. If you're stealing a significant amount of electricity, they could probably know it within an hour. And of course, the amount of electricity you get is directly dependent on the time. So that means an hour is probably not going to get you that much electricity to begin with. So anyways, but that's one of the things you do. And what's kind of neat about this is my former wife used to work in a gated community up in the mountains of Chapel Hill. I know they're hills, but still it looks kind of mountainous. And at one point, they call it the poor section of the wealthy gated community. The poor section where I used to run, these wires were maybe 20 feet off the ground. And on a particularly humid day, I could feel my arm hairs standing up, and you could hear popping noises because the voltage was so high, the air was about to break down on it. And you hear it was just so cool. But yeah, you could literally just hold a voltmeter up and put a probe towards the ground and another probe towards the sky, and it would read a voltage across it just from the air. So that's kind of neat about those power cables. So you can get near them and do neat stuff like that, but be advised, these are super, super dangerous. In fact, one of the, you can look at a video on a guy on TikTok, it's like Grandy 210 or something like that. He teaches this kind of electricity stuff online, I mean, for power companies. And one of the ways they work on these is they have a helicopter fly you in and drop you on it. Because it's not dangerous. 240,000, 500,000, 1,000,000 volts is not dangerous as long as you stay at 1,000,000 volts. It's when you connect that 1,000,000 volts to 0 volts that you become a really, well, at that point, you're just going to explode basically. But it's current running through you so badly that you're going to explode. That's not a good thing. right? But yeah, you can work on that all day long and it's relatively safe, but you know, switching from one wire to a slightly different voltage or to a significantly different voltage can kill you. So, all right, well, that's enough of the concepts, I think, for Faraday's law. And I really only worked one rotate. Well, actually, I worked a couple problems, one being the voltage divider, which is a useful thing to know about. The other being this, and then of course I did the simple rail sliding through a magnetic field. Those are like problems in your book. Every book has them. So definitely look at those. Look more at the examples in your book. And next time we're going to be doing basically just examples and maybe some more concepts. I need you guys to do a lot of practice on predicting which direction the magnetic field, or excuse me, the current induced will go. Okay. So you're free to go. I'll wait for the last person to leave and then I'll close up shop.
And we do have a
Professor?
lab today, correct?
Yes, we do have a lab. And regarding your midterm, I have a student still that hasn't taken it. Once all of them have been taken, I'll make a grandiose announcement. If you missed it, if you have a valid excuse, I can give you an extension to do it without points taken off. But if you missed it, or if you missed test 3, which I've noticed a buttload of people did, then I can open those back up for you, but you're going to get a 10-point deduction for doing it late. So you got to let me know if y'all miss something, and then, like I said, I'll make it happen so you can make it up. But you're going to lose 10 points. If you got an excuse, you know, you went to a doctor, you were sick, you were in a car wreck, you got a citation or whatever showing that you were in a car wreck at that time, any of that kind of stuff, I can verify. Then I can let you take it without points taken off. You folks are free to go.
Hi, Professor Younger. I had a question about mastering physics.
Yes.
So I gathered chapter 29 conceptual and homework we do next week, but chapter 18, 19 conceptual both in chapter 17, I'll say they're due on the 25th.
Right. That's not any chapters we haven't covered are irrelevant. Their dates are irrelevant. What it is the website makes me either it puts in dates for me or it makes me put in dates. And I don't necessarily always know exactly what the date's going to be. So I just leave them be until I get to them. So today we're covering chapter 29 and we've covered 21 through 29. So those are the only dates that matter at all. So don't worry about ever missing one we haven't covered. And remember, beginning of each class, I tell you guys what we are covering. So you should know roughly what chapter you're on at any point. So far, we've covered 21 through 29. So anything before or after 29, before 21 or after 29 can't be relevant to you as far as the dates go. Sorry about the confusion with that, though.
Oh, that's okay. Thank you. I know you've explained that like a bunch of times. I was just double checking.
Yeah, I know I know you're an overachiever and you want to make a good grade. So that's a good thing.
Thank you. I'll see you for lab.
All right, see ya.
I was just
Professor,
gonna say,
quick question.
Zach?
I logged on late today and I just wanted to make sure I didn't miss any major announcements at the start of class.
No, I was just telling everybody I was having some Zoom problems. That's about the only thing you really missed.
Okay,
Since you're here at the end, you heard about the final. William
Okay, thank you.
Ulrich or whatever your last name is. Ulrich.
Yes. In the grade book, you have the practice test worth an actual test.
That's it.
I think-
Yeah, that's gonna be fixed. If there's sometimes when I first make a practice test, it automatically puts it in one category errantly. So if you're seeing that, then it's good that you noticed it, but I'll go and check. I need to put all of them in a practice test. They're not going to count as a grade except in a way to help you.
Yeah, that actually wasn't my question. I just noticed it right now. I was looking in the grade book. My question is I'm sorry, I don't know how to phrase this. The electrical current going through a a power cable. Doesn't the flux field it changes every 60 times a second, right?
Yeah.
Because of the AC current going and changing. I remember this being said in one of my electronics classes a long time ago, but isn't there a phase differential between the flux and the current within the cable?
Yeah, in fact, that's what I was showing you with the graph that I made. You notice my flux was NBA cosine omega t. So when I found the actual voltage, that was sine omega t. So that was already a 90-degree phase shift between the flux and the EMF. And then, in fact, there's also going to be a phase shift between voltage and current given by Eli the Iceman.
Yeah, I wasn't sure if it is it a positive or negative 90 degree.
That's always a weird thing that I work out each time I cover it. So right now it appears that.
And I know capacitors do the exact opposite of it. It's just I forget what way it goes for AC current.
Yeah, so Eli the Iceman is what we use to remember those. So that means the voltage leads the current in an inductor. That's what Eli means. And then ice means the current leads the voltage in a in a capacitor. That's what ice means. So in this case, I think it's acting, if you say it's acting like a capacitor, then it should be the current leading the voltage.
Okay. Yeah, I was just a little curious.
Yeah. It's like I said, I always had a problem with that. It looks to me like, yeah, if we're only 90 degrees, basically the current, the voltage here is leading the, is actually, yeah, it's got to be, oh, that's what it is. Okay, I see now. If I move this graph, let me turn it on this for a second. Come on, internet. Okay, so I'm looking at these two graphs, and if I say they're only 90 degrees off, that means, you know, from here to here is 90 degrees. So the only way this can be is this is at t equals 0 and it's right here, whereas this is at t is 0, it's right here. So in fact, this one must be ahead by 90 degrees. So the current leads the flux by 90 degrees.
And it changes the equation from a sine to a cosine. Yep.
Yeah.
Okay.
Okay.
Makes sense.
Yeah, I always have a hard time working that out. I got to do it each time like that. Christian, Aiden, or anybody else have any questions?
Yeah, I had a question. So on Canvas, it says that the midterm doesn't have a due date, but it says that it's available on the 19th. Does that matter, or can I still take it? Like,
no, you were one of my special cases. So are you ready to take it now? I mean, not
I
right
either want
this
to take
instant.
it like tonight, or like my classes got canceled tomorrow. So if I could take it like tomorrow morning.
I'll set it available to you from right now till tomorrow at midnight.
Okay, thank you.
No problem. See you, Christian.
Bye.
I was just gonna let you know. I know you said you had internet issues like this morning or something. I don't know anything you might have done different, but the video quality is like way better than it's ever been. So I just want to let you know.
That's cool. Maybe they've been working on something.
Yeah, it's significantly better.
Yeah, but I just want to let you know. So you know,
Appreciate it.
if you had done anything that it worked, or if not, then I don't know.
Awesome. That's good to hear. Thank you, man.
Oh, I wanted to ask a second question. Sorry. For the midterm, the actual midterm, are you gonna do a like a grade shift or no?
No. You mean because there was a lot of low grades or whatever?
Yeah, because like the mean is like 60 points.
Yeah, that mean is that's actually a pretty good mean for the midterm, to be honest with you. I will address that probably in about probably Tuesday. I'll address it with you guys. But
okay.
Yeah, I'm not planning on curving it.
Yeah, I won't lie to you. I did get a 50 basically.
Yeah. That's more along the lines of what I expected for, I shouldn't say for most people, but for a lot of people at least. It's really a little bit earth shaking when you first realize how much you are sort of possibly relying on your extra resources when you're taking an online test. So I always see averages in the low to mid 50s on the midterm, and then they sort of get the hint and say, oh, well, I must be leaning too much on my resources, because they always do better in the final. Or a good fraction of those numbers that did badly. So, I have a thing I'm working out for you guys, and I'll let y'all know probably by Tuesday.
Cool. Just wanted to ask. I'm totally fine with the grade. It's just I wanted to know.
Yeah, yeah. Don't worry, Mr. Younger's got you back.
Well, thank you. Have a nice day.
You too,
And
Stuart.
actually, no, I want to see you in.
Oh
30
yeah,
minutes.
lab. That's right.
Or an hour and 30.
Yeah. See you, man.
See ya.